Welcome to the second video in the second unit of our semester, in which we're talking about acid-base chemistry. So in this video, what I'd like to try to start to do, although we won't finish this discussion in this particular video, is to answer this question. Why is it that acids actually have different acid strengths? We established that not all acids are the same in the first video of the series, so this will be the beginning of our discussion about why there are differences. And to get started, I want to actually do a little bit of practice. So I've drawn three different acid structures here: methane or CH4, ammonia or NH3, and water, H2O. What I'd like for you to do is just draw the acid dissociation products. So essentially, what would happen if methane acted like an acid? We should form two products, and I'd just like for you to draw their structures. Do that for all three of our different acids. This is going to be building up toward our skill of being able to predict the structures of conjugate acids and conjugate bases given the structures of the reactant acid and base. So go ahead and pause your video and populate this side of the equilibria now. So one way we can generate these products is to actually think about using mechanistic arrows as a guide for structural change. So if I'm thinking about methane, I know that for this compound to function as an acid, it must donate H+, which means that one of these carbon-hydrogen bonds is going to break. But because I'm donating H+ to solution or to a base or whatever, that means that the electrons in one of these CH bonds need to actually go to the carbon, not the hydrogen. So this arrow helps me to know exactly what to draw on the other side. So I'm going to have a carbon with three H's attached. I'll draw those in now. And then if I look at what I'm showing in this mechanistic arrow, there should be a lone pair that develops on carbon. And I know from my formal charge counting rules that this carbon is now going to be negatively charged. So the only other thing left that I have to draw is H+ itself. And that's it, I'm done. So I can do the other two acids in the same fashion. Doesn't matter which hydrogen you pick. I'm just going to use the one on the right because it's convenient. And the pattern is the same. Any acid is going to lose a hydrogen and gain electrons from the whatever bond was to that hydrogen. So here I'm going to have a nitrogen with now two lone pairs. Ammonia has one to begin with. And this nitrogen is going to be formally negatively charged. Just like before, I'm also going to end up with H+. And then finally, if I do this for water, this is probably the acid dissociation of the three that you're most familiar with. The idea here is that I would generate hydroxide, where oxygen starts with two lone pairs, ends up with three, negative, and H+. Okay. So there's a few things that we can point out right away. One is that if we start with something that's like a neutral acid, so for instance, the carbon or nitrogen or oxygen, if that's a neutral atom, and we actually use that as a site of acidity, then that atom will become more negative, and that's always going to be true. So the thing that loses the proton will become more negative. If it were neutral, it's going to become negatively charged. If it were positively charged, it would become neutral. That's more negative, right? Okay, so we've now essentially decided that these structures in this column here in the middle, these are our conjugate bases, which I'm going to abbreviate just conj, but that's for conjugate. And we don't really, I guess, have a conjugate acid in a meaningful sense. I guess it would be H+ or something like that, right? But we can see that these anions differ. They're structurally different. Okay. So the next thing that I'm going to do is I'm going to give you some pKa data. Now, even though I'm going to put the pKa data over here, which of these compounds, H+, this anion, or this structure, do you think the pKa really describes? So remember that we're talking about acid dissociation. These compounds are the acids. So if I were to write a pKa, it would be for one of the hydrogens of methane, or for one of the hydrogens of ammonia, or for one of the hydrogens of a water molecule. Okay, so here are the pKa values. Some of these are estimates, right? So treat them as approximate. So we'll say 50 for methane, plus or minus like 5, right? So this is kind of a crude estimate. Ammonia is going to be about 35, again, plus or minus several, maybe up to about 5. And then water, it turns out, is exactly 14. So that last number is exact. So the next thing that I want you to think about to reinforce what you learned in the first video is which of these three acids is the strongest acid. So pause your video and assign which of these three structures is most acidic. So we remember from the end of the first video that we can actually use pKa values to assess relative acidity, and we determined that as pKa gets smaller or goes down, acid strength goes up. So of these three numbers, 50, 35, and 14, 14 is the smallest, and that will correspond to the strongest acid out of my set. So we have to be clear here. I'm not saying water is a strong acid. I'm saying it's a stronger acid than ammonia or methane. That's typically how we talk about acidity. It's not about absolutes, it's about relative to other kinds of structures. So we know that our water here is the most acidic. And I guess methane would be the least acidic. So what's left for us is to actually attribute or correlate this observed difference in acidity to some kind of structural features in these equilibria, right? This is actually a very complex problem to do because these equilibria, like how much to the right or the left we are, which is really what pKa is describing, right? It's related to Ka, is impacted by a lot of factors. Things like temperature, things like the amount of solvent that's present, what kind of solvent it is, all of those things matter, but we can make a few simplifying assumptions. It turns out all of these values are measured under the same set of conditions. So same solvent, same temperature, same concentrations initially. So really we're starting to isolate things like structures of compounds. And what we're going to find in this video is that that's actually a driving factor for whether a compound is strongly acidic or not. Everything matters, but the structures involved in this equilibrium matter a lot. Now, it would be nice and probably intuitive to say, oh, it's the structures of the acids that make a big difference. And that can sometimes be true, but what we know from a lot of study and theoretical work is that for the most part, it's actually the structures of the conjugate bases that are going to matter the most, right? So this is a really important concept that I want to make sure that we get on the board here. So if we're going to say that differences in acidity are driven by conjugate base structures. All right, this is something that I would like for you to memorize, just like the relationship between pKa and acid strength. So this statement's really confusing for most people. It certainly was confusing to me when I was learning about this back when I was in college because it seems so counterintuitive, right? We're talking about acid strength, but we're analyzing a structure that we're calling a base. That doesn't seem to make sense. So I'd like to walk through this, hopefully make it a little bit more intuitive to you. So let's look at what's happening with one of our acids. I'm just going to choose methane because it's easy for me to reach this part of the board. It's kind of comfortable. So what's happening to this structure as it goes from acid to conjugate base is that it's serving the role as an acid. It's losing its proton to go from methane to CH3-, right? So let's do a little thought experiment. We're going to anthropomorphize this methane molecule. We're going to treat it like a human. So it has emotions and desires and goals and pet peeves, whatever. Why would this structure do this reaction? Like, there's got to be some reason. It's not just going to happen randomly. And it turns out that we could actually decide most of what molecules do with a very simple framework. Molecules like to become more stable. Essentially, this is how nature functions. Right? We're trying to make, at least in part, we're trying to make more stable structures if we can. So if we go from this neutral carbon atom to this negatively charged carbon atom, that's probably not awesome. I'm starting to build up a lot of electron density around this carbon. That's what the negative charge is telling me. And we know from our basic understanding of electricity and charged particles that electrons repel other electrons. This concept of repulsion is also going to be correlated with saying like electrons destabilize other electrons. Same idea. The repulsion is happening because the electrons are like, if I move a little further away from other electrons, I'm more stable. So what we could say is that like probably this is not a very strong acid, because if it were to act like an acid, if it were to actually fulfill that role, it would become the conjugate base, which is a problem because we're like dramatically destabilizing the structure of methane to do this. Why would it ever happen? Right, it wouldn't. And that means that it's very unlikely that methane will ever really donate its proton, which is another way of saying it's a weak acid, right? So it's not only that differences in acidity are driven by conjugate-based structures, it's actually that they're driven by the stability of those conjugate-based structures. So let's add that. Yeah, so what we now have is a framework to understand these differences in acidity. We're looking at, well, how good or how stabilized is the conjugate base that the acid could become. So if we look at our bottom molecule, water, we can see that it's a lot more acidic than methane, and we can correlate that to the fact that its conjugate base, so this would be hydroxide in the case of water, must be quite a bit more stabilized than CH3-. That's essentially what the pKa will actually tell us. So that's worth writing down. pKa data tells us about relative conjugate base stability. Stability. There we go. There's my spelling mistake for the video. Perfect. So the last question then that we need to deal with in this section of the video is, well, why is it that the hydroxide anion is more stable than the methane anion? We can basically say that that is true because of the pKa data and what we know about relative acidity, but we are not yet ready to explain why this anion is more stable than that anion. So what I'd like for you to do is actually pause your video and come up with a hypothesis, right? It's okay if it turns out to be inaccurate. You probably could generate more than one hypothesis. That would be rad. But what I'd like for you to do is come up with an explanation. So why is hydroxide more stable than the methane anion? So I'm hoping that when you generated your hypothesis or hypotheses, you started by looking at what's different structurally between the CH3 anion and the OH- anion. So you could find a few things. One would be the number of hydrogens that are still in the structure, so 3 versus 1. You could also count lone pairs. 1 lone pair here versus 3 lone pairs in hydroxide. And then the final thing you might notice is like the nature of the atom, or what kind of atom is present, so carbon versus oxygen, right? Those are all going to be structural variables. In principle, any or all or some of those variables could actually impact relative acidity or relative stability of these anions. And it's probably true that they all do matter, but one of these variables matters a lot more than others, and that's actually very common, right? One of the skills that you'll develop over the course of the semester, or begin to develop, because it takes a number of years to really get good at this, is to use what you know about the driving forces for phenomena. So like, why is stability a thing at all in chemistry, right? And actually correlate that to some of these variables and reject others on the basis of your understanding of the system, right? This is a skill that's really challenging, but it's also really valuable. So we're going to practice that a little bit over the course of the semester here. This is an example of where we'll do that. So when we think about stability of molecules, we're literally talking about charge stability. To the degree that I can get electrons to hang out with protons, that's a good thing. That's stabilizing. You might talk about those as attracting each other, but remember, attraction is the same. You come together because you're stabilizing each other. On the other hand, we know that electrons repel other electrons, and so that should be destabilizing. So if that's our framework, which is essentially the core of structural chemistry, like for every aspect of biochemistry and chemistry and biology, right? We could actually reject the variable of the number of electrons or the number of lone pairs, because if I look at this oxygen, I've got 3 different lone pairs on oxygen. So they're going to be very close together, repelling each other and destabilizing each other. On the other hand, I've just got 1 lone pair on a carbon, right? So now all that the electrons here could do is interact with electrons in CH bonds, which is going to be like a little bit like not as bad as lone pairs because the electrons in this bond are a little further away from the carbon than they would be if they were like localized lone pairs. Okay, so here's why we can reject this lone pair hypothesis. If I've got all this electron repulsion here, that should make the conjugate base really unstable. And if this conjugate base is really unstable, we should have an exceedingly weak acid. But that's not what we see. Like we would be saying, well, the more electron repulsion we have, the more stable the conjugate base is, and then the more acidic the compound is. That doesn't make sense, right? The hypothesis would, or the prediction that the hypothesis would make contradicts the data. Right? So we can reject this lone pair counting idea, at least in this set of examples. We could also maybe question the idea that it's the number of hydrogens that matter. Why is it that more hydrogens versus fewer hydrogens would actually like impact the stability of electrons? I have no reason to be able to explain that. On the other hand, I know quite a bit about carbon atoms versus oxygen atoms because I took Gen Chem 1. And I know about things like atomic radius, I know about things like electronegativity, and both of those might matter. So if we think about carbon versus oxygen with respect to atomic radius, they're not that different. You probably have predicted that oxygen would be a little bit smaller than carbon, but the changes are pretty minor, right? These two elements are in the same row of the periodic table, and they're fairly close together. So if we're not seeing big differences in atomic radius, why are we seeing huge differences in acidity? Again, not consistent with the data. The other thing we could consider is electronegativity. So carbon is a lot less electronegative than oxygen, right? So Fonkelnebersch. O is the second letter, carbon is way down near the end of the word, and if you actually use electronegativity scales, oxygen's electronegativity is around 3.5, whereas carbon's around 2.5, and the scale is from 0 to 4. So there's a very big difference in electronegativity between these two atoms. That does seem to fit the data. If I've got a large difference in electronegativity between these two elements, and I'm seeing a large difference in acidity for those structures, maybe those could actually be related to each other in a meaningful or a causal way. So let's actually now make sure that this electronegativity argument passes the sniff test with respect to our understanding of charge. Well, what does electronegativity mean? You probably heard something like, well, it's the amount of pull that an atom has, or it's like the way that it polarizes a bond, and those are true, but I guess the question is, well, why would an element exert a strong pull on electrons in a bond? Well, the electrons are going to sidle up next to that atom because they actually are stabilized by being closer to that atom. And if we actually think deeply about electronegativity, we find that highly electronegative elements like oxygen or fluorine, those are elements that are very small, and they also have a large number of protons in their nucleus for their row in the periodic table. That's why you basically have your most electronegative elements in the top right corner of the periodic table, as small as you can get, and the most number of protons you can get before you have to open a new valence shell and go to the next row of the periodic table, right? So that's like the best case scenario for electrons. They can get close to a relatively large number of protons. That would also apply to our lone pair or our negative charge stabilization for these conjugate bases. Carbon, not being a particularly electronegative element, is not very good at stabilizing a lone pair. Its nucleus isn't that attractive to the electrons. On the other hand, is oxygen much more electronegative, which is another way of saying oxygen does a great job of stabilizing electrons. So if we're actually building up electron density on oxygen to become the conjugate base, that's okay, because oxygen is able to deal with it. And this is because of electronegativity. So one thing that we could say here is that the more electronegative the element that's gaining a lone pair here, the more stabilized the conjugate base. So increasing, I'm going to abbreviate electronegativity as En. Hopefully that's okay. Electronegativity is a long word. So as we increase electronegativity of the atom gaining the lone pair, the conjugate base stability goes up. So there's this relationship. As I make the atom that's gaining the lone pair, so like oxygen or nitrogen or carbon, as I make that more electronegative, then the conjugate base stabilization goes up. And if I know that the conjugate base stabilization is going up, the corresponding acid should be getting more acidic. Well, that's exactly what we see. So carbon is the least electronegative out of carbon, nitrogen, and oxygen. That means that this structure will be the least stable conjugate base, and therefore this acid that it's related to will be the weakest acid in the set. Looks great. Nitrogen is the second most electronegative, or the middle in our set. And let's see, this nitrogen is correlated to the nitrogen in ammonia, and ammonia is the middle acidity in our set. Check. And then water, the conjugate base has an oxygen that's gaining a lone pair. That's the most electronegative of my three possible elements. So water will be the most acidic out of my set. Check. So this concept applies for all structures, at least at some level. This is going to be one of the rules that we're going to use to parse relative acidity and to explain trends in anion or conjugate base stabilization. So this one is worth committing to memory, and whatever phrasing makes sense to you. Okay, so in the next section of our video, we'll be looking at another one of these rules. We'll look at more data. Now we have our framework about conjugate base stabilization and how that relates to pKa's. So we're going to use the data to derive our second rule. In this section of the video, we'll be looking at three new acids, or I guess two new acids. We'll look at water, and then we'll look at hydrogen sulfide along with hydrogen selenide. So selenium, Se, versus sulfur versus oxygen. And so rather than drawing a whole acid-base equilibria, I've just drawn the conjugate bases for my three different acids, the hydroxide anion, this sulfur anion, and then the selenium anion. One of the things that you might have noticed in our previous section is that all three acids made H+. Well, duh. These dissociation reactions, that's always going to be true. So if they all make H+, H+ itself we can't use to explain any differences in acidity. It's a constant, right? So you also can see the pKa's for these three different acids. What I'd like for you to do is apply the first rule that we've developed, so that was what we just did, to this set of data. You might need to look up some electronegativities. I'd strongly encourage you to get at a periodic table and see where oxygen, sulfur, and selenium are with respect to each other on the periodic table, if you don't already know. And what I want you to do is decide, does this rule apply to this set of acids? So to evaluate this, we would first need to know the electronegativities of oxygen versus sulfur versus selenium. And we could either do this using numbers, or we could use the periodic table to assess relative electronegativities. I'm going to do the latter. So we know that oxygen, sulfur, and selenium are all in the same column of the periodic table. And oxygen's at the top of the column, and then sulfur is one step down from oxygen, and selenium is one step down from sulfur. So what we know is that oxygen is the most electronegative of our three non-hydrogen atoms, and selenium is the least electronegative. So if I actually look at what's happening on my conjugate bases, oxygen, sulfur, and selenium, those are the ones that are gaining a lone pair. They're becoming negatively charged. And it looks like this rule is actually directly contradicted. What we actually see is that the least electronegative element, selenium, apparently has the most stabilized pair of electrons once it becomes its conjugate base. Weird. So clearly, just having this electronegativity rule is not enough, because we see some cases where that rule breaks down. So we're back to the drawing board about structural variables. Well, here all three of our molecules, have two hydrogens to start and one hydrogen in the conjugate base. So that's a wash. They all have the exact same number of lone pairs. So that's a wash. All we're left with is the nature of oxygen versus sulfur versus selenium. And we just rejected electronegativity as a tool to explain what we're seeing in the data. But we could bring back atomic radius. So we know that oxygen versus sulfur versus selenium, those are all in different rows of the periodic table. So oxygen, if we think about that like an orange or an apple or something of about that size, then sulfur would be like, I don't know, a small beach ball, much, much, much bigger, because we've expanded our valence shell. We're like to the next principal quantum number. And then selenium, it's like we're doing that again. So this would be like, I don't know, a small geodesic dome house or something. I mean, so much bigger than an oxygen. So atomic radius does also appear to correlate. We rejected it in the first set of data because it changed very little between carbon, oxygen, and nitrogen. But here, atomic radius is changing dramatically, and so that can have an influence. So we could say something like the atomic radius of the atom gaining a lone pair, as that radius goes up, whereas like selenium would be the largest, then our pKa apparently goes down. So we have this other kind of rule. It doesn't have anything to do with electronegativity and everything to do with atomic radius. Like any rule, it's helpful for us to make sure that it makes sense relative to our understanding of first principles, or in this case, our framework involving charge stabilization. So we would need to explain why atomic radius makes the electrons on selenium a lot more stable than the electrons on the oxygen. There are a lot of different competing explanations for this type of phenomenon. The one that I think I'll present to you involves kind of a simple model. It's a little bit of a simplification, but I think it works well for getting a basic understanding here. And that's that if we have a very small sphere, like an oxygen, and we take 6 electrons and place them on the sphere, the distance between those electrons is going to be relatively short, right? We'll have the 6 electrons on a small surface. That makes them really close together. And we know that electrons repel each other. So to some extent, packing them on a small sphere is detrimental. They see each other, they repel, and they destabilize. If I place them on a really big sphere, like on selenium, so imagine placing this on like a giant beach ball sphere, just huge, right? I'm still just having 6 electrons. So if I put those on like, I'm just going to line this up with a camera, there we go, like really, really big distances between each of my electrons, because the surface has gotten a lot bigger, that should actually be, in a sense, it should be stabilizing relative to the oxygen, right? I'm actually removing a lot of electron-electron repulsions by spreading the electrons out over a larger surface. So that does seem consistent with our charge stabilization model for what we're seeing here. Okay, so you probably have noticed that these two rules will contradict each other all the time, right? So if you applied rule 1 to these acids, you would have been like perfectly wrong, totally like inverted your pKa scale, I guess. If you applied this rule, the second rule, to the data set that we looked at in the previous section of the video involving methane and ammonia and water, you also would have been perfectly wrong. So catch-22, like this sounds great, there goes my grade. Yeah, it's complicated, and in a lot of cases you do need to take both of these into account, especially if you're comparing like atoms that are gaining electrons, like for instance oxygen or sulfur, if you make a diagonal comparison. So if you're looking at your periodic table, if you were to decide something like, well, oxygen versus phosphorus, right? So it's like you're both moving one column, like, or one row down, but you're also moving one column to the left. So in that case, both of these rules will apply, and it's really difficult. It's basically impossible to use them qualitatively to make predictions. You just don't know which of these two rules is like more important. But there are lots of scenarios where you can essentially use one or the other. So if you're looking at comparing elements within a single row or across a row, rule 1 is going to dominate. So this is going to be our row comparison. And if you're looking at elements in a single column, like we're doing in this example, then it's going to be the second rule that's going to matter. So this is our column comparison. Any other situation, any of those other diagonal analyses, or where you're like hopping over big parts of the periodic table, you really need to do the experiment. You would need to measure the pKa values to know like which of these two rules is going to be more important. And I'm never going to ask you to make those kinds of predictions. The only thing that would be possible would be if I gave you the pKa data for two structures for like some kind of diagonal comparison, and then I asked you to make some kind of an argument, right? So then you know the result and you're back rationalizing, which is an important skill also. Okay, so that concludes this video. We're going to keep talking about this notion of why acids differ in strength, because it turns out there's going to be more observations to add. But I want you to go ahead and get started thinking about these ideas in isolation before we move on to slightly more complex looking structures and different kinds of features that involve more than just a single atom that's gaining a lone pair.